BC span is 20 feet. EI is constant. So as this is flexibility methods, what we do is first we determine the statical indeterminacy of the problem. Here it is 2 degrees indeterminate. So 2 redundant actions should be chosen. And we will choose these redundant actions such that our calculations are easy. Next slide now, if you see the vertical reaction at B and the vertical reaction at C, we choose those one as our redundant actions. Now, how we fix the direction of these redundant actions? That is arbitrary. You can choose them in the upward direction. You can choose them in the downward direction. So here you can see AR1 and AR2. These are the redundant actions, and we have chosen them in the downward direction. So downward direction is becoming our positive sign. So AR matrix is now AR1 and AR2, which are unknown at this stage, and DRS corresponding to them now in the original structure, we see if there are any preconditions. If there are no preconditions, straight away we record them as 0, 0, and if there are any preconditions, we record them accordingly. So now here we don't have any settlement at B, no settlement at C. So we record them equal to 0, 0. So DRS1 and DRS2, these are the initial support rotations and translations corresponding to the redundant actions 1 and 2, which are 0 in this case. So that's why this matrix is becoming 0. Now remember, at frequent intervals, I'll be stopping my lecture and I'll be asking you that if you have any questions. So in that particular time, you can ask me questions if you need any clarifications or anything. So then you can turn on your mics and then you can ask me. Other than that, your mics should be also turned off. Now, we are making this as a statically determinate structure, which will be known as release structure. So here you can see A, B, C. At B and C, we have removed the redundant actions now, and you can see this cantilever as our basic determinate structure. Now, here this note is important. When the support settlements and redundant actions are in opposite direction to each other, they will give DRS sign to the DRS sign. And if they are matching, so it will be a positive sign for the DRS values. Step number 2, we are coming now. Here we will generate our DRL matrix. Here it is written DRL matrix. So how it is going to be generated? This will be the release structure under the actual applied loads. Now for the beams, I'll be using the conjugate beam method corresponding to AR1 and AR2. If we can find out the displacement due to these actually applied loads, that will give us the DRL1 and DRL2 values. Here you can see this is the basic determinate structure, and it is loaded with 1.5 kip per foot and then 20 kip of pointed load. Conjugate beam method, now you will have to visualize, and you need to refresh your memory again about the conjugate beam method. First, we need to make the conjugate beam. How it is made? It is having the same length as that of the original structure. You have the length now. How to describe the support conditions, the boundary conditions? So fix will become free in the conjugate beam and free will become fixed in the conjugate beam. This way we make the conjugate beam. Now once the conjugate beam is formed, we load it with the M over EI diagram, and that acts as a loading for the conjugate beam. Now we have a fully described conjugate beam. Now once we have this, so at a section, if we find a moment, that will give you the deflection in the actual structure. And in the conjugate beam, if we find a shear at a section, that will give you the rotation or slope in the actual structure. So that is the now corresponding values. From here now what we do, we draw the bending moment diagram. How the bending moment diagram is drawn, we go back to this slide now. At each now section, what we do, we find out the bending moment values. Directly you can do it like this 300, how it is coming. It is coming from 1.5 times 20, which is becoming equivalent pointed load here. So 1.5 times 20 is 30 and times the moment arm now. So moment arm is 20 divided by 2, which is 10. So 30 multiplied by 10, it is giving us 300 kPa. Similarly, here you can find out, here you can find out. Now looking at the loading diagram and looking at these values now, you should be able to draw the bending moment diagram. So here it is becoming the bending moment diagram now. Here you can see this 2 degrees, it is coming from this UDL, no loading. So this is becoming first degree, no loading. This is becoming first degree, and here we see the bending moment values and divided by EI. This I value was 2I, so this will become 300 divided by 2 EI in that case. So this will become 150 divided by EI. So you have to be much careful while writing this M over EI values. Next now, here now we see this is the conjugate beam here, fixed to free and free to fix, you can see, and it is loaded with the M over EI diagram. So here you can see now. Now corresponding to AR1, if we can find out this moment now, that will give you this DRL1 value, which is the deflection corresponding to AR1. And let's see if we can find out the moment in conjugate beam, that will become the DRL2 values. From these simple geometries, you can find out those values. For moment, you will need the force that is load in this case, which is the area under this. You see these vertical lines, which is a trapezium. Here this is a trapezium, and here we see 2 degrees curve. So if we can find the load and the moment arm, we can find out the moment at any section. So W1, W2, W3, and then X1, X2, and X3 if we can find out. So next slide, this W1, W2, W3, this is W3, not W1, W2, X1, X2, and this is X3, not. So you need to make this correction. And here how we find out for trapezium and the area under any curve, what is the relation between the area under this N, which is the degree of the curve, and the area. So here you can see it. So already we discussed this in the classroom. Next now, DRL1, now you can see W1 times X1 plus 10 plus W2 times X2. So this was the moment at the AR1 location. You need to write this down, and I'll go back to the diagram from where we can verify this. DRL1 is equal to W1 times X1 plus 10 plus W2 times X2. So let's go back there. If you have written this, let's go back here now. This is, so here we are taking the moment about MC in the conjugate beam. It will be equal to W1 times X1 plus this distance, which is 10 feet. So W1 under the bracket X1 plus 10 plus W2 times X2. That was we had here. Here it is. Similarly, DR2, this should be equal to MC in the conjugate beam. And when we simplify these numbers, DRL1 and DRL2, we have these numbers, 156685 and 446685 divided by EI. Now, the compatibility equation was involving 4 parameters. One was DRS, which we found in step number 1. One was the AR, which we declared unknown in step number 1. Other was DRL, which we found in this step number 2. The only thing now the parameter left is the flexibility coefficient value, so which we are going to find out in the third step. So third step is coming now. Compute the values of rotation or displacements in the primary structure corresponding to the redundant locations When primary structure acted upon by the unit actions are compute the values of flexibility matrix F. First, apply a unit value of AR1 at reference point 1 and compute the values of flexibility coefficients F11 and F21. Already we discussed what is the first subscript showing and what the second subscript is showing. If you see here, the first subscript, which is shown by the white color in this box, so it refers to the position of interest where we are finding out the displacement. The second subscript is showing to the unit load position where the unit load is applied. So this is the meaning of the second subscript. Now here, in this case, we will apply this unit load turn by turn corresponding to the redundant action. The structure is statically indeterminate to 2 degrees. So 2 times we will be revising this analysis process. Here AR1 was in the downward direction. It was at location B. So here you can see now 1 kip we are applying in the downward direction. This is the conjugate beam now. In order to draw the M or EI diagram, we are finding out the moment values here now. So 1 times 0, it is giving you 0 kip moment. The load cannot be transferred to the right because it does not have any support. So it is traveling to the left now. And what will be the moment at the left? It will be 1 times this distance, which is 20 feet. So 1 times 20 is equal to 20 kip foot. Here, the conjugate beam you can see again, fixed to free and free to fix. Now here, this is M over EI diagram, 20 divided by EI, and it is becoming a straight 1 degree because here we have 0 degree. So this is becoming 1 degree. We don't have any load here. The shear force will be having 0 degree and it is 1st degree. Now, F11, which is deflection corresponding to AR1 due to unit action, means it is a flexibility coefficient, and F at 1 due to 1, F at 2 due to 2. Now we can find out. We already know the relation between the actual and the conjugate beam values. Now, first we need to find out the load of this triangle, which is half of base times this perpendicular. So half times 20 times 20. So it is becoming 200 over EI. And we can find out the distance also. From this less load intensity, 0 load intensity, the movement arm will be 2/3 of this horizontal distance. So 2/3 of this 20, which is 13.33. So 200 times 13.33, that will become our F11. And F21 will become equal to 200 divided by EI times 13.33 plus this distance, which is 20 feet. So that will give us F21. Here we can see these numbers. This is how we find out the W1. This is how we find out the X, which is 13.33. F11 we found 200 divided by EI times 13.33. And F21, which is W times X plus 20. So here we get this number. So this way now, if you see F11, F21, which is actually the first column of the flexibility coefficient matrix that is constructed. In order to construct the second column of this flexibility coefficient matrix, now we need to apply the unit redundant action corresponding to AR2, and here we see now their situation. This is AR2, so corresponding to that in the same direction, 1 kip is applied. Now to draw the moment M or EI diagram, we need to find out the moment value. So 1 times 20, this is becoming 20 kip feet, and 1 times this 40, it is becoming 40 kip feet. And here you see the conjugate beam, and this is now M or EI diagram. The conjugate beam loaded with the M over EI diagram. Now this hedge portion, this is showing you that when you are taking now the moment about B now, so only this hedge portion will be included. And its weight or its area is becoming 600 over EI. This is when we take the moment about B. But when we take the moment about C, then this whole triangular portion will be included, and its area, which is in turn is its weight, W2, it is becoming 800 divided by EI. So remember, when we are finding out moment about B now, so 600 divided by EI and times this distance from its centroid to B, that is becoming your MB now, and that will give you your value of F12, and that must be equal to F21, which we found in the previous slide. Now, MC you can find out very easily. It will be the area of this triangle times 2/3 of this distance, which is coming 26.67. So that way you can find out F22. So we go to the next slide, and there you can see all these numbers. So here you see now F12 exactly, it is coming out equal to 4/6 divided by EI, and F22 is becoming this value. Remember, F12, it is not matching the F21. It means there is something wrong with the calculation, so we need to revise. Next, now we write very nicely this flexibility coefficient matrix. This is the flexibility. EI is taken out as common, and 2 666, and here we have 4 6s, 4 6, and 21, say 31. Now, when all the three parameters, these one, F values, DRS, and DRL values, these are found, we can find out the AR values now. So in step number 4, we solve the compatibility equation now. So coming to the compatibility now, here you can see this is the inverse. We took the inverse of those big numbers, so that is why it is coming out in these decimals. DRS1, S2 were 0 because we were not having any pre-settlements. And then DRL1, DRL2 we found out, so we are just trying to remember this minus, these values are by default there in the equation. But in actual, if you get the DRL value, let's say that is coming out minus, so you need to put that minus with this number, so minus and minus will become positive. Now, when we solve this, so it is AR1 and AR2 are coming minus 29.36 and minus 11.76. Minus signs are showing now that the initially assumed directions of AR1, AR2, those were wrong. We need to just reverse the direction. So here you can see now AR1, we are reversing the direction. Instead of downward, we are making it upward. The magnitude is 23.36. 29.36, and AR2, it is 11.79. This is 76 and this is 79, not a big difference, but this should be exactly this value. Now, rest of the problem you can solve by the equilibrium, but you can do it by the matrix approach also. For that case, now we go to step number 5. And step number 5, now how we find out the member and actions, we assume at certain cross section. Now let's find out these. This is going to be your choice. And now in terms of the availability and ease, you can find out the values. AM is the member and actions, which is here. Let's this AM1, AM2, AM3, and AM4. AM4, if you see, already we found this value, which was 11.76 or 79, something like that. Here, if you want to verify that value, let's you have kind of time, so you can verify this value by using this approach. Otherwise, you don't need to find out this thing again. So AM is equal to AML plus AMR times AR. Now, from where AML values will be coming, these will be the corresponding values from the analysis of the determinate beam where we applied the actual loads. And remember, from the same we calculated the DRL matrix. So we calculate from the same the DRL matrix, and from there you can find out the corresponding AML values. AMR values will be coming from the analysis of the determinant structure where we applied the unit load corresponding to the redundant actions. First column will be generated from where we found the F11, F21, F31, like those values, the first column of the flexibility matrix. Second column of the AMR will be generated where we will provide the unit redundant action corresponding to AR2, and from where the second column of the flexibility coefficient matrix was generated, and so on. AR already we found, so now it's simply the matrix operation now when you do this, so you can find out all the member end actions, which will include the shear forces, the moments at the member ends you can find out. And after that, what we do, we can write those on the structure. The structure is fully analyzed, and then looking at the loading diagram and these shear force and bending moment, we can very easily draw the shear force and bending moment diagrams. Now compute AML values. Here now you can see AML values. This is now the basic determinant structure under the actual applied loads, 1.5 kip per foot and 20 kip. Here you can see. Now, how we analyze this basic determinant structure, which is just a cantilever structure. Here, we don't have any support, so 0. The load is traveling towards the support now, where A, we have a fixed support now. So just to the left of this section, what will be the reaction? It will be 1.5 times 1. So 1.5 kip in upward direction, and just to the, this will be just to the right of this section, which we are taking at 1 foot. And just to the left of that section will be 1.5 in the downward direction. Here at B, if we want to find out the reaction, so this will become 30 kip. From where this 30 kip is coming, 1.5 times 20, which is 30. So it is in the upward direction. Just to the left of this section at B, it will be 30 kip in the downward direction. Now, under this one, you can find out, but we don't need to because we don't have any vertical reaction here. We have a moment here only. Here, what will be the reaction? It will be 1.5 times 30 plus 20. So this is going to be, so this is kind of finding out the shear force and bending moment values at various sections. These moments already we have found, and you can verify this. So from here now, you can see your positive directions are coming from here now. AM1, 2, 3, 4 in upward direction. Now AM5 counterclockwise, AM6 if it is to the left. So clockwise, and if it is to the right of the section, counterclockwise, this is my positive. Similarly, AM7 also, you can see what is the positive direction. So now we will be comparing with this one. If our AML values are coming in the same direction, so it means those are positive, otherwise negative. So here now it is in the upward direction, so it means it is plus 50. Here it was downward. Already we show it in the upward, but with this negative 30, it is showing that if we make it in downward direction, then we don't need to show it as minus 30. Then we will be showing it as a 30. To the right of this section B, we have 30 in the upward direction, so it is 30. Here we have 0, so 0 is recorded here. This is in the same direction of AML5, so it is 1100 plus. Here, this 600 is in the same positive direction. These positive directions now, they are decided from the AM positive directions. If they are matching positive with AM, if not matching with AMs, then negative. AM7, you can see it is 300, so 300 is recorded here. This is how we make the AML matrix. Next, now we need to find out the AMR, and in AMR, the first columns we need to construct. So compute the AMR values. How those will be computed? First, apply a unit action at redundant location 1 and then at redundant location 2 as shown below. Redundant location 1, this was B location in the same direction, 1 kip is. And if we analyze this determinant structure, the values corresponding to the AM, those will be becoming the AMR values now. So AMR 4, you can see 0, AMR 3.1, it is 0, AMR 4.1 down, so it is initially down. So this is minus 1 kip we are showing here. AMR 1.1, it is 1 kip in the upward direction. AMR 5, it is 20 kip feet. Here it is 10, 1 times 10. So this is 10 and here it is 0. So this, very quickly now we can make our first column of the AMR values, which will be 1, minus 1, 0, 0, 20, 10, and 0. Then the second column, to generate the second column corresponding to AR2, we apply the load. We analyze the basic determinant structure and the corresponding values, which are AMR 1, 2, 2, 2, 3, 2. We find them. This is the analysis. Now the corresponding values, if you see 1, 2 is coming 1, 2, 2 is coming minus 1, and R 3, 2, it is 1, and 4, 2, it is minus 1. Similarly, 5, 2, 6, 2, and 7, 2, you can see. And here now, these values are recorded here. Let's verify this AMR 7, 2. So if I go to the previous one, AMR 7, 2, it is in the same direction, so plus 20, and that is why this plus 20 is recorded here. Now, AR value is already known, so now we are in a position to solve this matrix multiplication and addition. We can process these matrices. So to process now, you see all these values. These are the AR, and remember with the original signs, minus minus, this AR is coming. When we multiply them, we get all the member and actions now. 8.88 corresponding to AM1 now. So here we record this. 11.12. So shear just to the left, it is 11.12. Just to the right, 11.24. Then at C, we have 11.76. Then moment, it was 42. This was coming 46.4. It should be with minus sign there. Let's see now. This is here, minus 46. So minus 46.4. This is why the direction is reversed now. This direction is reversed. And here AM7 plus 64, so plus 64.8 we record here. Now, this is a complete analyzed structure now. And if you add them up now, look, this one, 11.12, shear to the left, shear to the right. So this will become reaction at the support, which was, I think, 30 point something. So this 29.36, how much it is coming? This 11, and this is 29, and this is exactly, it is coming the same number, 29.36, 29.36. And to the right, you see 11.76. So this is 11.76. Now, when we have the loading diagram and we have these member and actions, now we don't need to do anything else. Now we can draw the shear force, and only this point, now you can find out the distance, you can find out the bending moment value here, and you can record this. So this is the completed now shear force and bending moment diagram. Now, before going to the next problem, where we will be involving the displacements now, which will include the translation at the supports and the rotations at the supports, I'll take a pause and I'll ask you if you have any question now. You can turn on your mics and you can ask me questions. CR, where are you? Mr. Ejaz is asking something?
Yes, sir.
Okay, yes, Mr. Mohammad Ihtisham Arshad.
Yes, sir.
So how do you find this lecture now online? Are you comfortable?
Yes, sir. अगर आप इसको सर अगर आप प्रॉब्लम को किसी सॉफ्टवेयर पे इस्तेमाल करें या जो साइड बोर्ड होता है उसके ऊपर करें तो ज्यादा सर कंफर्टेबल होगा। इस तरीके से सर थोड़ा कम समझ आता है।
नहीं, ऑलरेडी तो मैंने वो क्या हुआ था ना, आई डिड दिस इन द
ये
क्लासरूम
तो ठीक है
ऑलरेडी,
सर, ये तो
सो
ठीक है
हाँ, तो ये
सर,
ठीक है।
ये
सो
तो ठीक
नेक्स्ट
है।
next difficulty if you have that should be coming from the coming problems. Now at this stage you cannot tell me that this is not a good way to teach, right? I walk you through in the classroom and now this was kind of repetition of that thing, so you should be at least comfortable with this problem. In next classes we will be finding out how to facilitate you in learning. Okay, okay Jaz, now
ओके
you were having any question?
यस सर। सर ये जो हमने एएमआर जो फाइंड कर रहे थे और जो सेकेंड रिडंडेंट एक्शन पे हमने यूनिट लोड अप्लाई किया ना सर, तो वो वाला
हाँ,
स्लाइड जरा आप वो वाला स्लाइड सर आप जरा डिस्प्ले करें।
अच्छा मैं कर लेता हूँ। अच्छा, दिस इज ना, यहाँ पे आप पूछ रहे हैं?
यस यस
अच्छा,
सर। तो सी सी पे जो हमारे पास ये वन किप के अपोजिट जो रिएक्शन आएगा वो वन किप नहीं होगा। यहाँ पे आपने सर -1 लिखा है, तो फिर वो तो उसका डायरेक्शन अपोजिट हो जाएगा, तो फिर ये कैसे उसको अपोज करेगा?
नहीं उसी पॉइंट पे जब आप आ रहे हैं ना, ये अपोज नहीं कर रहे हैं, उसी पॉइंट पे तो नीचे आ रहा है ना, एट सी पे, राइट? एट दैट लोकेशन इट इज इन द डाउनवर्ड डायरेक्शन। ठीक है, तो सी पे ये नीचे की तरफ होगा, एंड जस्ट
सर
टू द
तो
लेफ्ट इट विल बिकम इन द अपवर्ड डायरेक्शन देन।
सर तो सी पे जो वन किप लोड अप्लाइड हो रहा है इसको अपोज नहीं करेगा ये वन किप?
तो जस्ट टू द लेफ्ट ये अपोज करेगा ना इसको।
तो फिर सर ये तो +1 किप होगा ना सर, आपने -1 किप लिखा है, तो फिर ये तो इसकी डायरेक्शन तो फिर नीचे हो जाएगी, तो फिर ये किस तरह अपोज करेगा?
नहीं, आपका पॉजिटिव डायरेक्शन जो था ना एयर टू का, दैट वाज इन द डाउनवर्ड डायरेक्शन। वन के अगर आप देख लें, दैट इज योर पॉजिटिव डायरेक्शन।
तो यही तो कह रहा हूँ सर, लेकिन आपने वैसे भी ऊपर मतलब शो किया है ना, ये -1 किप जो आपने लिखा है तो ऊपर शो किया है ना, तो फिर इसमें तो -1 लिखने की जरूरत नहीं थी ना, माइनस लिखने की जरूरत नहीं थी, सिर्फ वन किप मतलब सही होता ना।
नहीं, तो ये इसी लोकेशन पे तो नीचे आ रहा है ना।
सर ये तो मतलब वन किप ऊपर से डाउनवर्ड लग रहा है, तो वन किप नीचे से सर ऊपर नहीं लगेगा, नीचे से ऊपर लगेगा ना सर?
जस्ट टू द लेफ्ट जब आप आएंगे सी से ना, तो वहां पे ऊपर की तरफ लगेगा। अब सी लोकेशन पे यही नीचे आ रहा है।
ठीक है सर।
ठीक है ना, जस्ट क्वाइट एट द सी लोकेशन इट इज इन द डाउनवर्ड डायरेक्शन, तो वो तो आपका पॉजिटिव आएगा, लेकिन जस्ट जब आप लेफ्ट को आएंगे ना इस सेक्शन के, तो वो आपका ऊपर की तरफ होगा।
ठीक है सर।
ठीक है, और हम सपोर्ट रिएक्शन कहां पे, ये शेयर कहां पे ले रहे हैं? जस्ट टू द लेफ्ट ऑफ दिस सेक्शन सी ले रहे हैं।
ओके सर।
ठीक है, तो वो ऊपर की तरफ होगा, तो वो तो आपका नेगेटिव डायरेक्शन हो गया ना इस केस में।
ओके सर।
अच्छा, नेक्स्ट देखें, हमारा हमारा साइन कन्वेंशन क्या है? हम ऊपर की तरफ लगाते हैं ना। Okay, let me take this phone call.